Hello, I'm Tom Hebb, and I work on Red Team X at Meta. We do vulnerability analysis of external products, and you can see some of our work on the blog that I've linked here. This is the third and final part of the video series I'm doing on firmware analysis. So this is about finding bugs in the code that isn't your operating system. And you can see sort of the whole process in theory outlined in the first two parts that I've recorded. And in this part, we're going to be giving a sort of real-life demo of one of the chips on the Quest 2 and what's in its firmware. So I have a Quest 2 right here, and we're going to be analyzing the firmware for one specific chip in here, which I did mention before, but as a refresher, that is the C-Media 7104 chip. And what that chip does is all of the audio processing on the Quest 2. So it's a digital signal processor first and foremost, and it does things like echo cancellation on the audio, and noise reduction, and spatial audio, and all sorts of microphone and speaker handling. So this connects to the main chip through I2S audio bus and runs its own firmware, as any chip that does this level of processing would have to. And previously, we showed that it is one of those chips that has firmware loaded from the kernel each time the kernel boots. And so obtaining that firmware isn't too difficult. So let's jump right in and take a look. Right here, I have my laptop with an Oculus Quest 2 connected. We can see it shows up in ADB. It's just in the normal Android. It's not in any special mode. And when we go into the shell, we can look at some of the firmware directories. So I happen to know that the C-Media chip firmware is at vendor firmware, I believe. It's right here, cm710x.bin. Unfortunately, Android has some SE Linux restrictions that makes it a little bit harder to read firmware when you're not running as root, which you aren't going to be on devices that, on most consumer devices. You see, you can try to read it, but it actually just says it doesn't exist, even though it shows up in the listing. Luckily, there's a trick on Android to get around this specific issue, and that is to do the vendor shell. So this looks identical, but now when we go into vendor firmware, we can see all of the metadata here. So this is the trick I'm going to use to read out the firmware, and we can just do that with a single ADB shell command from the outside here. So ADB shell, we're going to say /vendor/bin/sh, run a command, and that command will be cat/vendor/cm710x.bin. And close that quote, and then we can write this to cm710x.bin on our local machine. So that's spawning one shell, spawning another shell, piping the contents of the file out through both shells, and then we save it locally. So now we have it right here. You can see the size matches, and just like that, we've obtained the firmware. If we want to go back one step and talk about the enumerate phase, this chip was both shown in the photos that I showed back in part 1 of the Quest 2 mainboard, so you can find it that way. And you can also find it in the device tree. So in the shell here, we see the device is named Hollywood. That's the code name. So when you go to the Oculus Quest kernel source, look for Hollywood audio, then you scroll down, and you find this CM710X. It also conveniently says it's hooked up over an SPI bus for control. The compatible string right here, which we care about, we take that and we can search for it elsewhere in the kernel under the drivers. So then we go here, and this is, I'm shortcutting a bit, I'm not actually searching, but this is where it is. And you can find this file, which has that magic compatible struct with the matching string that tells you this is the driver that handles that device. This file specifically, this SPI, doesn't have much. The bulk of the driver is in another file here called cm710x.c. And when you look in this file, you can see lots and lots of code that you don't really want to read through. But you can remember, request firmware. This is the function that is used to load firmware for any driver in Linux, practically, that loads firmware every time it starts. So you search for this, and sure enough, we find it. We actually find it twice. And the second one is the one we care about. The first one is just calibration data. It's not any executable code. It's just a bunch of fixed values. But this one here, cm710x firmware, this here is exactly the name of that binary file that we found. So there we go. That's how we enumerate it. That's how we obtain it. Now that we have this file, what might we do? We could start by reading the code, but let's say we just want to jump right into it and try to figure it out ourselves. So what I'm going to do is I'm going to load it into Katai struct, like I showed in part 2. And what's on the screen right now is just the built-in PNG image parser and a sample PNG image for Katai struct. You can kind of see how it's working, but we don't want this. We want to parse our own firmware. So what we'll do is first we'll make a new KSY format. So CM firmware, we'll call it. Create that, and we get a new file here, and you can see all this parsing goes away. And then we want to point it directly at the file that we just obtained. So now we have this firmware on the right, and then our specification of that firmware on the left. And so I usually just start at the beginning at this point. Like in Ghidra, when you're analyzing an unknown binary, how you'd start at main and just see what it's doing. Just start at the first byte, see if you can figure out what's happening. So what I notice here is that the first 3 bytes of this file have the text CMR, readable characters. And to me, that looks a lot like a magic number, one of those things I mentioned in the last part that identifies a file. This is, there's a magic number for ELF, a magic number for PNG, and this is how utilities like File and Bimwalk identify those files. And vendors want to make sure the file that they're loading as firmware is actually firmware, so they put magic numbers in too. So let's just take a guess. We'll start writing this specification. And this is the great thing about Katai struct, is that you can just take guesses really, really quickly. Everything live updates as you type here. And so you can delete things, add things super quickly. So I'm going to add a new item called magic with content CMR. And then, boom, just like that, it shows up. If I change this to be, CME, something else, it suddenly says can't parse because it's not equal to what it expected. So it does some validation as well as parsing. So then the next thing I notice is that we've only got 3 bytes of magic here, and usually things in files like this are aligned at least on 4-byte boundaries, and that's just because they're generally dumped straight out of C structs in whatever code reads and writes them, and C doesn't like misaligned accesses like that. It's not easy to make a misaligned struct, and it won't. There's no reason to do it. So my guess, my next guess is going to be that there's some unknown byte. We don't care what it is, but we're going to say it's of type U1, a 1-byte unsigned integer, and it'll just be something that's, to be determined later. So now we've got through the obvious first 4 bytes, and we're trying to figure out what else is here. We can see there's some amount of data here stretching down to about address 290 here, and before you have a block of zeros, so there's some kind of split between separate things, and then at 43C the data starts back up again. But honestly, this data doesn't look very obvious to me. It doesn't make a lot of sense what it is. I can kind of see that there are these columns of zeros. There's a pattern. 0 here, 0 here, 0 every 4 bytes. So I might guess that these are 4-byte long numbers. So I might say here we're going to have numbers. We don't know what they are, but just to get them over here so we can see them more clearly. Each one is a 4-byte unsigned integer, and we're going to say that they repeat. So repeat based on an expression, and that expression can be 100 numbers just to start, just to get us a sense of what's here. It's going to tell us I didn't specify an endianness, which is true, so I'll just put a default one in here. Most things are little endian in my experience because they're just written straight out of C structures. So we'll guess that. And here we see a whole list of numbers. Many of them are pretty aligned, lots of zeros in there. But they all have these weird ending bytes. Some of them are super small, but not all of them. So it's like, it's not super clear to me that there's any structure or data here that I care about or can understand. So I could keep banging my head on this, try going further in the file. But what I'm going to do now is just go back to that source code that we already have and see if it can give us any hints. Sometimes a file like this is loaded straight to the device, and the device does all the work of parsing it. But in some cases, part of the header is parsed by the kernel first. So if we go here to the main file where request firmware gets called, scroll down, we can see what happens next. We have a function called cm710x firmware parsing. That seems very promising, so let's jump into it. And very clearly at the beginning of this function, it is checking that the first 2 bytes are C and M. So we were exactly right that it started with some magic. If that magic isn't there, it says firmware image not correct. We weren't right that the R, the 3rd byte, was also a magic. In fact, that is a count of something here. Then there's another count in the next byte. So it's CM and then 2 single byte counts. So for now, we'll just say change our magic to CM. We can just go and update this super easily. We'll say ID, count 1, call this count 2, and then give this a type of U1 just like that. And now you see it split into 2 instead of just being 1, and we have our magic correctly set to just those first 2 bytes. Then we keep on going. We see there's some address, some 2-byte address in 4 and 5, and then 6 and 7 are more single byte values. So that adds up to 4. So our we're still 4-byte aligned. It does some validation. It calculates a checksum, and then it keeps on going. And I'm not going to take you through reading all of this code because it takes a while. But I assure you that going through that makes it clear what many of these things are, and you can reflect them in a Katai struct specification, just like I've done in this one that I've already written. So you have the same thing here, the magic CM, but now we have those counts filled out. We have the 2-byte address we saw. I even put in a validation statement for the address because it's the firmware, or the driver expects it to always be 8. And then we've done some more complex things like having something that starts at an address specified by the file itself instead of just being a linear sequence continuing on from everything else. So we read the data address here, and then we instantiate this subtype firmware data at that address. So this all turns into this very nice tree structure down here. You see all of the things in the header, then you see this instance we've created, and then you have all of the different pieces of that instance that are parsed out. I2C commands, all of these things here, these turned out to just be sort of hard-coded commands that are sent in order to load firmware, and so we don't really care about those. What we do care about are these DSP blocks, which, as I discovered, hold the firmware itself. So each one has a very simple header. It has the address that the firmware is loaded at, which, as you remember, is very important for analyzing the firmware. It has the length that follows, and then it has just a big block of data at that length. And we can guess that this data is just the raw machine code that's going to be loaded at that address. So I didn't know this was the base address. There's no documentation telling me that. But I was able to guess because it's a large 32-bit, very round number, and it comes right before code. And so there's a lot of sort of guessing involved. And then as you get to the later steps, you'll figure out if those guesses were correct or not. But in this case, let's just move on and see for ourselves. So what I can do is I can go here, I can right-click and say download. That downloads this section of the file. We don't need to download them all. This one's tiny. if we were doing a full analysis, we'd want to place them all, but for the demo, I'll just do these two, the first one and the big one here. So now you can go to your static analysis tool. You can go to Ghidra or your tool of preference, say import file, and choose that file. We're gonna cut out a view of my file system here while I navigate. We're going to navigate to those files we downloaded. We'll start with the one at the beginning and select it. And then here it says raw binary. There's no ELF, there's no anything. And what comes with that is that it doesn't know what architecture this code is for. So you have this whole list. Is it ARM? Is it x86? Have we discovered that? Not yet. And the file holds no clues to what architecture it is. So how can we figure out what architecture this code is? We can go to data sheets. We can go to publicly available information. So if I go online here to the CM7104 product brief on CMedia's website, this is all the information I was able to find for this chip. It has a very brief introduction paragraph. It says the features, but sadly, it doesn't say anything about firmware. And it doesn't say anything about a CPU. It doesn't say anything about an architecture, well, except the product architecture. So it was, it's not clear. And I tried common architectures. I tried ARM. I tried MIPS. And nothing was really working. And I almost gave up, actually, until I thought to go to this other page on CMedia's website for the CM7120, a very similar chip. This is actually the chip that's in the Quest Pro, I believe. And this has a little more information. It's not a lot more, but it has a block diagram even. So this is a more complete product page. And crucially, one thing that it mentions is that the chip has a 10 silica Hi-Fi 3 DSP core. So now we have a product name, a core name to go off. This is where some domain-specific knowledge comes in handy. A 10 silica DSP core is meant for highly parallel DSP code, I believe. It's not really there for general purpose firmware. But 10 silica, as a manufacturer, is also famous for their Extensa instruction set. Cadence has since acquired 10 silica, but Extensa is a pretty common instruction set because it's used in a lot of hobbyist chips, like the ESP32 uses Extensa cores. And because of that, it actually has a decent amount of tooling available for it. So I was like, hey, let me try the Extensa. Let me see if this is Extensa code, because I know that they're already using 10 silica IP. So I did that. Just a random or not so random guess, but often reverse engineering is just a matter of trying lots of things in a row. So Ghidra doesn't come with Extensa support, but there's a plugin that's very easy to install. So when you select that, it now is able to import. You can click OK, but I do need to do one important thing, which is set that base address. So we think from this file that the base address is 50000 and not 00000. And that will affect references in the code to other code and to constants and stuff. So we need to make sure to set this because we can't change it later. So I'll say OK. Go through the normal process of opening this up, doing an analysis. And nothing shows up. It's finished the analysis, but there's nothing here. That's because, unlike an ELF, a raw binary doesn't have any information on its entry point or where the code starts executing from. So Ghidra isn't going to guess that something is code when it might not be. It's just going to leave everything undisassembled to start. But it's very common for execution to just start at the beginning or at a nice round offset in memory, because that's what the CPU cores know how to do. They just start at some address and run code from there, and that's usually the beginning of RAM. So we can just guess, and we'll disassemble from the very beginning. And now we get a really, really good sign. So we can see that this hasn't just disassembled to random nonsense or invalid instructions. It starts with a jump instruction, which is good because usually other areas at the very beginning of memory are reserved for things like vector tables and other metadata. And so it's jumping right over all of that up to here. And then here, not only do we have a lot of instructions, loads and stores and stuff like that that look plausible, we also have nice round addresses here. And we have a large amount of disassembly with pretty complex structures like loops that mirror one another in structure. And so this is pretty this is pretty guaranteed to be the correct architecture that we've guessed. It would be incredibly unlikely that some other architecture would happen to disassemble a code that looks this reasonable. So we can drop a function here. We can say f, call this main because it's the entry point, we think. And then we keep reading, but at the bottom we see this halt bad data. And usually that's a bad sign because what that means is that Ghidra found something that it doesn't think is an instruction. And if your code has something that's not a valid instruction, how can it actually be code? Luckily, the extensa architecture is one of the exceptions to this rule because extensa is designed to be extended, as its name implies, and for manufacturers to put in extra specific instructions for their use case. So this might be some DSP-specific instruction for this audio codec that isn't in the Ghidra plugin. So for this, we can just kind of guess, and we can keep disassembling later on. And we see after that one unknown instruction, we get more code that looks reasonable, and we have this infinite do loop, which is also a hallmark of firmware because if it ever stops executing, if it ever stops looping, it's just going to run off the end of memory and start executing garbage. So firmware will almost always be enclosed in just a big do while true loop, and we see exactly that. So at this point, we have gotten to the point where we can just start disassembling this. And you can use the memory map window here to do these markings. So for example, I mentioned in part 2 that if you don't want, if you know that some code is just the executable code and doesn't have any data, you can mark it as not writable, and Ghidra will do extra optimizations in the decompilation. You can go and add other segments, and you can map them, for example, to a file on disk. And so I'm not going to bother doing all of that. I'm just going to open the one that I have done ahead of time. And in this one, I have done that. So I've loaded up all of these different segments from the source firmware file that I found. I found what looks like a ROM segment. I found data, which is sort of writable and readable, just where it stores global variables and stuff like that. And then you can see that now we have a lot of functions that have been found and that call one another and have cross-references so you can see what calls them. And you have functions like this one, verbose terminate handler, which actually calls a print function with a readable string. And if you go and search for this function online, you will find that it corresponds to a function in the standard GNU libc++, and it's almost identical in terms of its structure. I gave it that name. It didn't have the name just in Ghidra. It was named generically like all these other functions. But because the code structure was so similar, it's checking if an object is null, and then inside it's reading a struct field. It is I'm not sure what the CXA demangle is for, but then it prints this function. It has an if-else, and when you go back to here, you can see there's that print, there's that if-else, there's the check for null, there's the field access. And so now that you have this, you can start going backwards. You can look at the cross-references, see what calls it, and look for functions that other functions in the source code, the libc source code that call this function, and then you can start sort of building the tree up from the bottom and making sense of all this firmware. And you can find where it reads and writes peripherals, where it actually communicates with the host, and start finding bugs. So that is a real-life example of how to go through this process and analyze some firmware that has an unknown file format, an unknown architecture, and get it to a point where you have readable decompilation. All right. And then these are some resources. They're going to be linked in the description. These are write-ups from various folks and organizations about reverse engineering firmware. They're all really good reads, and if you want to see more examples like that demo, I'd highly recommend you look at them. And that concludes part 3 and the whole video series. So thank you for watching.